Hi guys, I am Dr. Nanda Balaji. Today we are discuss about the topic of quantum mechanism, introduction to the black body radiation. What is a black body? An idealized object that absorbs all incident electromagnetic radiation, irrespective of frequency or angle of incidence. It emits thermal radiation solely based on its temperature, making it a perfect emitter and absorber. And characteristics of black body radiations, three different types of characteristics we have there. One is continuous spectrum, and second one is temperature dependent, and the third one is material independent. In continuous spectrum, the emitted radiation covers a continuous range of wavelengths, not just discrete lines. Temperature dependent, both the intensity and the peak wavelength of the emitted radiation are directly determined by the body's absolute temperature. And material independent, the radiation characteristics are universal and do not depend on the specific material composition or surface properties of the object. In Rayleigh-Jean's law, in classical predictions, classical physics attempted to describe blackbody radiation using Rayleigh-Jean's law. I of lambda t is equal to 2 kt by lambda 4. This law works reasonably well for longer wavelengths but dramatically fails at shorter wavelengths. Planck's law, the quantum solution, Max Planck revolutionized physics by proposing that energy is emitted and absorbed is directly packets or quanta. I del T is equal to 2 hc square divided by del sorry hc square divided by del power 5 1 by e power hc by uh, lambda kt equal minus 1. This quantum hypothesis successfully resolved the ultraviolet catastrophe, accurately predicting the absorbed blackbody spectrum across all wavelengths. Lambda max T is equal to 2.898 into 10 to the power of minus 3 m by c dot pk. This law states that the peak wavelength of emitted radiation from a black body is inversely proportional to its absolute temperature. Hotter objects emit radiation at shorter wavelengths, while cooler objects emit at longer wavelengths. Example, red light or infrared lights. In Stephen Boltzmann's law, as P is equal to psi A T power 4, where P is equal to total radiant power, A is the surface area, T is the absolute temperature, and psi is the Stephen Boltzmann constant. This law highlights the significant increase in radiative power with even small increases in temperature. The Stephen Boltzmann law quantifies the total power radiated per unit surface area of a black body across all wavelengths. In experimental setup, it kind of four different types of setups we have. One is cavity furnace, and second temperature measurement, and third spectrometer analysis, and fourth data comparison. First one, cavity furnace. A preciously heated cavity with a small aperture is used to simulate an ideal blackbody source. Temperature measurement, high precision temperature sensors monitor and control the cavity's internal temperature to ensure stability. Spectrometer analysis, a spectrometer measures the intensity of the emitted radiation across various wavelengths from the aperture. Data comparison, the measured spectrum is then compared against Planck's law predictions to validate the theoretical model. And key applications of blackbody radiation, astrophysics and cosmology. The cosmic microwave background radiation perfectly matches a black body spectrum, providing crucial evidence for the Big Bang theory. Temperature measurement from industrial pyrometers to medical thermometers, blackbody principles are used to non-inversely determine temperature based on emitted radiation. Infrared cameras, thermal imaging devices detect infrared radiation emitted by objects, allowing visualization of heat patterns for various applications, including security maintenance and medical diagnostics. And these are the further